In these recordings I will cover chapters 2 and 3 kinematics, and we'll do a number of problems. And the way I'm going to do that is that I'm going to read through the problem. I'm going to look at what information is giving. I'm going to jot that down, and then I'm going to set up the problem. And just before I actually calculate what the answer is, I will stop, because that's what I require of you, that you're able to plug in numbers and come up with a correct result. Later on, I will continue doing that with setting up the problems, because that's really the crucial thing to do that many people taking a physics class have trouble with. How do you actually start? So that's why we'll do this over and over again. Later on, I require that of you too, but I probably will continue to set up the problems as well to give you hints. Okay, anyway, let's start with the first one here. It says the land speed record of 13.9 meters per second for birds is held by the Australian emu. An emu running due south in a straight line at the speed slows down to a speed of 11.0 meters per second in 3.0 seconds. So what I'm going to do is, so there it's running south, that's why I drew it the way I did it, so 13.9 meters per second, and because it's south I will call it minus. That's also why I did it, so that we can look at the negatives and positives correctly. Then this one here, it has slowed down to 11.0 meters per second, and then the time it takes to do so is 3.0 seconds. So that's the information we have so far. In part A, it asks, what is the direction of the bird's acceleration? Well, the bird is running south, and then it has slowed down. That means that the acceleration has to be in the opposite direction. So the acceleration is going to be up or due north. So acceleration is north. Then it goes on, part B, assuming that the acceleration remains the same, what is the bird's velocity after an additional 4.0 seconds has elapsed? In the second part it says, assuming that the acceleration remains the same. So eventually down here in the second part I would have to plug in some number for the acceleration, but it's not given in the problem, and it sure looks like in the first part of the problem that's what we have to calculate. So I'm gonna write a question mark. We're supposed to come up with this one here, and now I'm gonna write what is given. The initial velocity is minus 13.9 meters per second. The final velocity is minus 11.0 meters per second, and the time is given 3.0 seconds. Looks like we're gonna come up with two significant figures when we're done. Now I have to look for the equation that I can use among the four kinematic equations that are supplied in the chapter, and it definitely has to include the acceleration, and it should include some or all of the other information. It should not include the distance that the emu ran, because that's not given, that's not implied in the problem at all. So I have to eliminate those equations that incorporate distance. The equation to use, therefore, is 2.4, which is velocity equals initial velocity plus acceleration times time. And I'm going to solve for the acceleration. So it's going to come out to velocity minus initial velocity divided by time. And you would have to follow the algebra that I did here. Get the V0 over there divided by time, because that's required of you in this kind of algebra-based physics class, that you know how to do the algebra. This is just an underline here, maybe a little bit too long. As I said, I'm not going to calculate the answer. That's up to you now. to plug in the numbers and come up with the correct answer. I'm just going to point out that here we're subtracting the larger negative number from a smaller negative number, so it means we're going to come up with a positive number in the denominator, divide by a positive time, so the acceleration is positive. And that makes sense because we decided earlier that the acceleration in fact is pointing north. That means in a positive direction. So it actually came out of the equations quite naturally. Okay, in the second part, the additional information that is given is 4.0 seconds the emo runs on. What we have given now is the initial velocity at that second part, and notice that as the emo continues on, it's the 11.0 meters per second that now has become the initial velocity because we're starting a new part of the problem. And then the acceleration, I should write in a number, but as I said, I'll leave that up to you to calculate that, so I'm just going to make a check mark that that is given. And then it says, what is the bird's velocity after an additional 4.0 seconds has eliminated? So here's the question mark, what is that velocity? And it turns out, as far as the equation is concerned, I use the same kind of equation, 2.4 v equals v0 plus at, and plug in the numbers and you're going to come up with something, because everything on the right hand side is given. Initial velocity, now the negative 11.0, acceleration that you come up with here, and time of 4 seconds. Next problem is, in getting ready to slam dunk the ball, a basketball player starts from rest and sprints to a speed of 6.0 meters per second in 1.5 seconds. Assuming that the player accelerates uniformly, determine the distance he runs. So from rest means that the initial velocity is 0. So that's implied information, or by looking at the text, from rest means initial velocity is 0. Sprints to a speed of 6.0 meters per second, so that's the final velocity. In this case, they don't say if it's left or right, so I'm just using left to right to keep positive numbers. In 1.5 seconds, just if I can, positive numbers are a little bit more convenient. Assuming that the player accelerates uniformly, determine the distance he runs. Okay, so question mark here. And the acceleration is not given, so we need an equation that definitely contains x and some or all of the other information. That equation is 2.7. For example, there is actually another equation. No, that's it. That's the only one we can use. So x equals 1/2 v0 plus v times time. Notice that everything is given, so you can readily compute the result.